Good morning, everybody. So we'll start today's session with Vinod's topic on image selection, initial model generation, and movie processing, which includes the topic that is mentioned in the book, which is conical tilt and projection matching, getting the first model using conical tilt and projection matching. And I'm sure you will agree with me. We had a excellent talk by him yesterday, and the practical sessions are going very well. Reliance sessions, which is being conducted by him and Nitish as well, who is helping him. And I'm sure you will enjoy today morning's talk by him and Monideepa, who is going to give a talk on point group symmetries. And afternoon, the Reliance session will continue. Hope you will enjoy today as well, like as ever. Okay.
Okay, so shall I start? Hey, good morning all. So thanks for coming again. I think you must be very tired, but you have to go for another 5 to 6 days. I'm leaving tomorrow anyway. So
That's why I'm saying you will enjoy.
yeah. So yesterday I was speaking to a lot of people, and then they felt that there was a lot of repetition. So I thought I will change the topic of initial model generation and expand it to include some thing about more about what kind of images you choose, and then you have been hearing more about movies and processing and so on, what they mean and how you process and how you get higher resolution using this movie processing. So again, I made some of these slides today morning. Luckily, I had them on my laptop, so it was very easy. So the three topics I thought I will go through was image selection, and then how you make the first initial model from images, and then how you deal with movies. So these three will be one. So what is a good image? So if you are a new user, you're putting your protein solution on a grid, you're going to look in the microscope, what is a good image? So in ideal case, you should have high signal to noise ratio, which means the background should be minimal and your particles should be visible against the background, and it should be monodisperse, homogeneous particles, evenly spread. You saw yesterday in the images of beta gal how it was. So you could see a lot of particles, they were separated and so on with different views. And they were in random particle orientation. So these two are very important. And then, like we discussed yesterday, you should see tone rings when you do a Fourier transform of these images. Here it says to Nyquist limit, at least to certain resolution, so that you are confident that the imaging is good. But in reality, you have noisy images simply because we use lower dose. And then there's a different level of heterogeneity and orientation bias. Again, these are all covered yesterday. And because of CTF, you also get some artifacts. Okay, so this is an example of a bad image and its Fourier transform where you don't see any rings. What happens if I don't see a tone rings? Where could be the problem? So the first thing you want to look is, was the microscope working properly and properly aligned? So this can be done because we use grids which also have carbon. So you can actually go to an area where there is carbon, and then you can take an image, and then you should see the Fourier transform when you are on the microscope, so that you know it's properly aligned. So during data collection, at the time of data collection, you have to make sure that everything is properly done before you start data collection, because it's easy to get a lot of data, but they may be very bad. So in particular, if you have a small proteins like 100 or 200 kilodalton in unsupported ice, which means that you don't have any support, just on water which is frozen to give ice, then they are weak scatterers, so you will not get enough CTF rings. So the way you can overcome this problem is, so this is an example of quantifiable carbon. Here is the hole, and there's the carbon here. And what we do during freezing is that you put your protein, and then you blot, and then you freeze to get reasonably thick or thin ice, depending on the diameter of the particle. And then instead of exposing, say for example, on the center or the whole area here, you can have in the imaging areas a little bit of carbon so that you tend to get tone rings from this area, and then that will help you, will give you confidence that your imaging is right. So in automated data collection, this kind of approach can also result in taking multiple images on the same hole, thus thereby increasing the amount of images you get. So the other thing you can do is, so for example, the protein you're working is from natural source, or you can't express, or it's in very little amount, then what you can do is you can add a thin layer of carbon on top of this quantifoil, which means that you need only 0.1 or 0.2, even sometimes very less. So then they are attached to the carbon, which gives not only the tone rings, you can see them very nicely, but the amount of protein which is less is also makes it advantageous. The only issue is that you have a lot of background. So if you had a very small particle like 100 or 150, then the background from carbon is very high. So alternatively, you can use things like graphene or graphene oxide, with single layer of graphene or graphene oxide, which are transparent to electrons. They do the same thing. But getting particles in the right orientation or right distribution in graphene and graphene oxide is still kind of a trial and error, but that's something to keep in mind. Okay, so what is a good distribution of particles? Here there are two examples. One of a 26S proteasome from Paula da Fonseca, from whom I took a lot of slides. So this is complex one which I have been working. So you can see that they are reasonably well distributed, and you do have a lot of different views in both of them. So in the case of proteasome, one looks always for side views. The top views don't give much to the reconstruction. So these are examples of reasonably good distribution and particles, and they are big, so you have a lot of contrast. And in the case of complex one, I use very high dose, I think about 60 electrons for taking the image. As you will see later in the movie processing, you can discard the last frames which are radiation damaged. Okay, so again, going back to tone rings, and one of the important parameters is to get the optimal ice thickness during freezing. So you can't have too thin ice, because the number of particles then goes down, although the tone rings looks reasonably good, which means that if you had less number of particles, then you need to collect a lot more images. That can be very painful if you are limited by microscope time. So in ideal situation, again, it depends also on the magnification, how many particles you get, and the field of view. So this example is from the different region of the same grid. So a grid can be 200, 300, or 400 mesh, will have a lot of grid squares. And the way it plotted, and when it freezes, you tend to have different thickness of ice. So within a grid, in different grid squares, you tend to have different thickness of ice. So during data collection, it's important to identify the right ice thickness so that you don't get thin ice or thick ice. So thick ice here is an example. You can see the particles, but you can see the power spectrum here is worse than what you have here. So this also adds to a lot of noise. And in this case of proteasome, you can see that the top views start appearing in thicker ice also. And the other thing to remember is what we call beam-induced motion or drift. You can see here you have nice circular tone rings going all the way to the edge of the power spectrum, but here you see it in one direction, but it's absent in the other direction. So this is very common in microscope which have a side entry holder, because they are prone to external factors like vibration or airflow, or even you moving in or out. So then you tend to get most of this. But most of the recent microscope which have an autoloader, and where the specimen is isolated from the environment, it's more stable, and most times you get a lot of good images like this. So that's drift. And then here is an example of astigmatism, where instead of having round, you have it elliptical. So this, in theory, correctable, but it's better to avoid. So all these things, it's better to minimize during microscopy rather than dealing it later during imaging. I thought I will also put an example of this one, which we call charging on specimen. So if I go back to long way here, so one of the things you have to remember is if you just had ice without any carbon, then if you had a beam just covering only this area here without touching the carbon, then what happens is that then you get a phenomenon called charging, which is what you saw in the image. That's why whenever you take an image of a specimen just with ice, then either you take one image covering the whole of the full hole here, so that the beam touches all around the carbon, or you take images like this where some of the beam is touching the carbon and the rest in here. So this charging is very bad, where you can see that some of the particles you can see, but here it's kind of blurred. This is very difficult to recover, even with alignment and movie programs, it's very difficult. So this was deliberately done just to show the effect of charging, because we were trying to see if you use a small beam, if you can get higher resolution. So this is an example of charging. So charging is different from drift. There are two different things. Okay, so now I think you have an idea of what might be good images. So during data collection, it's always good to spend a lot of time recording only in good areas, so that you don't have to go through a lot of images and then throw it later. Or you can do it manually and then look for good areas and collect. And the more important thing is, if you optimize your grids beforehand, that is going for a big data collection, then you know which kind of ice is going to give you good images, and then you can do automated data collection. So this way you can minimize the time you spend during imaging, processing, because processing, although as you saw yesterday, picking particles manually can be fun, but after say 100 images it can become boring. Then even when you sleep, you will start seeing particles all the time. Okay, so that's about images. So then I thought I will include some of examples of images we have taken so far. So starting from about 1.6 megadalton, these were all taken on direct detectors. So you see them very nicely. So that's pyruvate dehydrogenase and bovine complex 1. You can see them nicely. Then I go, this is very familiar to you. You have been looking for the past 3-4 days. So again, you can see them nicely here. It's 440 kilodalton. So when it go smaller, this is 230 kilodalton catalase, you can still see the particles. So one important thing to note in this is that during blotting, the central region of the hole here is completely devoid of anything, so it has become very thin. So what happens is that catalase, for whatever reason, it likes to kind of order in these arrays here when the ice gets thinner. So it forms this, and in some of the images you can see them forming kind of a circle, or in occasional cases it forms chains. It's like pseudocrystals. So as the ice gets thicker here, then you start seeing different views of the particle. So this you can encounter in some of your projects, and this is not very ideal, but it's useful to know that you can get things like this. Then this is a protein which is about 125 kilodalton. Again, you can see them nicely. It's a pentamer, and these two dots here are the side views of the pentamer. So if you imagine round 5 into 25 kilodalton protein, if it turns, then you have two side views. So the goal here in this project is to get enough information from these side views, which can be tricky. So if you can get that, then it's possible to orient, and you get a structure of these small ones. So that's 125. If you now go to a smaller one, hemoglobin, which you can take one drop of lead from your finger, and then you can put it on a grid, then you can see hemoglobin. So this was done with Richard's blood. We did see a lot of other things, but this image just shows hemoglobin. So that's as easy as taking from your finger. So if you go down to say about 14 kilodalton, which is lysozyme, you just see them as single dots here. So these, you can see them, but you can't orient them, which means that. So this we didn't attempt because we know it won't. Other people have done hemoglobin, and I think they can with faceplate. With the 125 kilodalton, I think we have reached something very low resolution. We don't have enough particles. Okay, so you can see that you can see the 14 kilodalton dots. So why am I showing this? Because you may be using, I don't know, a single chain antibody or something smaller as an additive or things to attach to your protein. So if you have in a kind of a, not in a stoichiometric ratio, but maybe some of the small ones are in higher concentration, then you will get this as background. So you may be able to still see your protein among this background, but uh, you need to remember that smaller ones tend to look like this. So nucleotides, for example, if you are working on a DNA binding protein, they may add also to the background. Or membrane proteins, detergent micelles can add background. Okay, so this is a table here which Richard and me made. So given the concentration of the protein and different molecular weight, so for a 800 angstrom thick ice, how much particle projection you should see in micron. So this is a rough guide. It's not like this is what you should see. But the idea is that, so the ones in red are too many particles, the one in blue are too less particles. So the one in green are the ones which are optimal for this different sizes protein. So this can be affected by a lot of different things. Maybe because your protein always sticks to the carbon, or the protein out of one single orientation, or the estimated concentration is too low, or like this. So most times the factor which affects is the glow discharge. So depending on how you do and when you did before freezing and so on, that's affected. And so this the number in bracket tells you the spacing between the two particles. So you can see that if you had a 10 kilodalton protein, you just need 20 microgram per ml, then you get about 100 particles per micrograph and so on. So if you had a 250 kilodalton protein, all you need is 0.5 milligram per ml and maybe, I don't know, 500 to 1,000 images to get to about 4 angstrom, and which will be like overnight data collection if everything works fine. But so this is just a rough guide, but you shouldn't treat them as kind of a standard. And if you are using carbon, thin carbon, then this all will not work because adding carbon makes it different. So you have to remember that. Okay, so that's about images. If you have questions, please do ask about data collection or. Sorry? Defocus. Yeah, sorry. I forgot. So you have been hearing about CTF a lot. So what kind of defocus do you use when you're imaging? And whether means the goal is to see the particles nicely so that you don't pick noise. So then you'll have to find a optimum defocus where you don't go too far and you are not too close so that you don't see. Like yesterday Elena was showing about this HIV GP160 where they were close to focus and then they did auto pick and then they started picking noise. Okay, so again going back to this to the size of the protein. So when you are starting a project, like I told yesterday, it's okay to use very high defocus and then very high dose so that you see what your protein looks like in solution and then also in a microscope. Then once you are confident that whatever you are seeing is truly reflective of what you did biochemically, then you can go back and then for larger data collection, a higher resolution, then you can. So theoretically, the lower the defocus, it's better to for higher resolution. That's simply because the tone rings which come from this defocus, they have to be accounted for and corrected. So if you have a higher defocus, then you're going to have a lot of oscillations. So with the field emission gun and larger, better coherence of the microscope, it is thought that you can use as high as defocus as possible, like 5, 6, 7 microns. But in practice, that's not true because the higher defocus may be introducing some other image blurring in the images. So one thought was that if you use a sufficiently large box, So if, for example, if you had a 1 megadalton protein, so there is a formula to calculate what kind of resolution you need to reach, what kind of defocus you are using, and then what is the particle diameter. Then you can calculate the size of the box you want to use to retrieve all the information that's happening with CDF. I didn't put a slide. Maybe I should have put. But anyway, so you can ask me about the range. So typically, one tend to use like 1.5 to 3 micron for reasonable data collection. I think with the K2 on the energy filter, then I think people tend to go lower. They have gone to, in recent high resolution structures of small proteins, they have gone to 0.6 or 0.7. I don't know if they can see, but yes, so that you can fill all the. Yeah, so he was asking during data collection, do you collect a range of defocus and what kind of steps do you need to use? Yes, you have to collect a range of defocus, and the steps depends on how you set up. Generally, people tend to use like 0.3 micron steps if they are doing automated data collection. They can start from say 1.5, 1.8, 2.1. So again, there is another parameter because you saw that you have a lot of holes, and the height varies a lot. So when you go from one hole to another hole, you hope that the height is not changing a lot. So if you set up like focus only every 5 microns, then you will think that it's 1.5. Maybe it's not really 1.5. Maybe it's 1.8 or 2. So you give kind of 1.5 to 3 micron in steps of 0.3. So that's how you do.
But but the focus very much depends on the size of the molecule.
Yeah, so that's what. So I was giving kind of a range.
Since, for example, for the proteins like you are showing, 25 megadaltons or 25 kilodaltons or 60, 3 microns probably not enough. What you would recommend?
Yeah. Yes, that's true. So for smaller proteins, which I don't recommend putting anything 10 kilodalton or 50 kilodalton now. You won't get a structure, but you can see them with 4 microns. So the size limit now is about 100 kilodalton, where people are getting very good resolution.
Some of the more latest high-end microscopes, can they do their own, once you set the defocus level on a certain grid or a certain hole, when they go to the adjacent hole, can they do it in an automated fashion?
Yeah, that's what most of the automated do. So you can set them to focus every image. Then you know that it's accurate. But again, that also depends whether the program is doing accurate defocusing. So that's one of the important things to remember. So if you do it every hole, then the number of images you get per hour is lower. So people tend to bypass by, if they find a flat grid square, then they just say do focus every 10-15 micron, and then it gives 1 image per minute or so. Then you get 60 images per hour.
Is it possible to measure data sets taken from different concentration?
Yeah, that's fine. That shouldn't be a problem. But I think a different magnification is still possible, but you have to do a lot of interpolation. Different microscope is possible. I don't know about different detectors. I wouldn't recommend, but you can try that too. Because Falcon is integration, K2 is counting. So in the end, they are just images. So you can separately refine them and then combine it later.
When we play focus, we have some problem with the magnification problem, right? At the same time.
What?
Magnification. The image will be shrinked.
So
that's
something again I didn't discuss about the changes in magnification or different images. People tend to ignore it. Most programs don't recommend refining magnification, But I think that's something going to be becoming important in the future. Because if you have different thickness or different height in the grid square, the magnification is going to be slightly different. But it looks like what we are doing is we are collecting a lot of images and then they just get averaged out.
So what's the Nyquist limits when you were talking about?
Oh, Nyquist, like Elena was telling yesterday, so if you want to reach 3 angstrom, then you have to sample already at 1 angstrom, only then you can reach. So if, like the data set yesterday, the beta gal we were plotting, it was bin, so it was 3.5 angstrom. So you can't reach beyond 7 on that data set.
Sorry, it's just a theoretical issue. Nyquist frequency is a is a frequency which corresponds to the double of the size of the peaks, and it came from the mathematical description that this is the highest frequency at which we have to calculate Fourier transform, and it will provide the back and reverse reconstruction without any damages in sense of the mathematical calculations. It's a mathematical definition of the frequency to which we have to calculate Fourier transform, and it was defined by the scientist whose name was Nyquist. And this is just comes from the how we can do digitization and calculation with high accuracy calculating Fourier transform. It means when you calculate Fourier transform, the highest frequency to which you have to calculate everything will correspond 1 divided by 2 pixel size. This is named as a Nyquist frequency. What I wanted to ask you about the anisotropic magnification.
Yeah. Well,
Anisotropic magnification is not the same like different magnification.
yeah, so that's a different, so, okay, so if you had some kind of, so we had, I think in one of the microscopes where there was a problem in the projection chamber, then you had a different magnification. So this was found by Nico Grigoriev in Genelia because they were trying to refine a virus. They were stuck at 7 angstrom for whatever reason, although they thought it should go better. Then it was due to the differential magnification or anisotropic. The one he is using doesn't, but Genelia has another CS character. I don't know about it. So Genelia has 2 of them. The one Nico is using doesn't have a CS character.
So I have one question.
Yeah.
As far as data collection is concerned, super resolution takes more time, right, in collecting data. So how actually your final, say everything else is ideal, whether you use super resolution or not, how the resolution should be final result?
I have not done the test myself, but people in Martin Street whom I spoke to, they said that at least when I spoke to them, they said it didn't make any difference between counting and super resolution because you are not actually refining in super resolution more. But I think they have now switched to super resolution.
Yeah, that's what
you get maybe a little bit of increase in DQE, which helps
Right,
with for
right.
small particles. Okay, so you have ice, which is a bad insulator. So if electrons come, it's going to produce a lot of electrons back because by breaking things. So if you don't have secondary electrons coming from neighboring area, it won't be neutralized. So you have charge there. That creates blurring. So when the beam touches the carbon, then the electrons coming from the carbon neutralize the charge in the ice. So that's how you get good images.
While picking for small particles, is it easy to differentiate heterogeneity and orientation? Like
No.
So is there a method to do?
Even for big particles, I think it's very difficult. Okay. Unless you see something falling apart, then you can say. But if it's like small movement, then you won't be. Maybe in 2D classification, you will be able to see them.
In extended data collection, before starting the main data collection, we can decide the dosage and exposure time.
Yeah, you have to do that here also.
How will you decide based on what quality? Which?
No, it depends actually on the detectors nowadays. Previously, in the old days, when you were using film mosicity, then you had to, that was limited by how much dose you could give, like 10 or 12 electrons. But now you can use whatever you like, 100 electrons or so. People have used it. But then you have to make sure that you fractionate these electrons or frames appropriately so that you can then align the individual frames and get back whatever you have done. So that you do it before you start. So that's an important thing also.
I had a quick question. So, is there a certain size limit on the smaller scale beyond which you would recommend having a thin carbon film so that that signal from the carbon can?
Yeah, so the smallest I have known is, I think about 200 people have done of an ion channel where they use thin carbon, and that seems to have worked for them. But I think anything below that, even for 200, I wouldn't recommend. So that's why people are very excited about graphene. So if they can find a way to make it working always, that it's possible that it will be working.
How do you use these terms DQE and sampling plus the particles which you detect? Is there any criteria which put these three together?
Oh, okay. So first thing you have to ask is what resolution I'm going to achieve.
From there
okay?
you start.
Yeah. So then, based on that, you decide what kind of pixel size you are going to use, and then based on that, you decide how many electrons you are going to use. So for each detector, there is certain number of electrons you need to use to get the best of the detector. So K2, because it's counting, you need to use longer exposure, but then I think the recommended is about 8 electrons per pixel per second. But people have used less, and they recommend that. For the Falcon, which is integrating, the recommended is about 50 electrons per pixel, and so on. And because Falcon is integrating, it doesn't matter the amount of electrons, like 40 or 50 or 60. With K2, it's recommended that you use higher pixel if you want to go for higher resolution. So for the beta gal, which was read 2.2, or Nico's virus, which is at 2.6, I think most of them, they use 0.3 super resolution and 0.6 physical pixel on the K2 to get those resolution. So the DQE is better if you go higher mag in K2. And for smaller particles, this may be of advantage because you are using the lower resolution information for orienting. So then you may get better orientation and better resolution.
But sometimes the impression is that if you go for higher sampling, that is a higher DQE, then super resolution comes in the picture. So
how do you mean? How do you mean?
No, what I'm trying to say is that the super resolution is better when there is a higher DQE. Is it true, actually, in terms of practical meaning?
Well, so I see the practicality is like this. If I'm going to take an image, how many particles can I get from an image? So if I'm going to get like 10 or 15, then it's a lot of work. You need a dedicated microscope to collect a lot of data, which can be very difficult. So then you drop the mag. It's not always you need 2 angstrom or 2.5 angstrom. So if you can address your biological question at 3 or 3.5, then you can just drop it and get more particles. So you don't need to go to that higher mag.
Is that the real trade-off?
Yes, it's a trade-off. So if you are really determined that I want 2 angstrom, then of course you can do that. You can spend a lot of time optimizing the grid, and then once you have it, you spend maybe a week of time on the microscope, then collect. I think that's the trade-off. But most times, we are always trying to understand what happens in the periphery there, where actually maybe the core is of high resolution, the periphery is lower. Yeah, that's the practical point of view.
Thank you.
Because most protein are not rigid, so they do a lot of things. Okay, so then we go on to the next topic, initial model generation. So you know from yesterday's lecture that before you start refinement, you need some kind of a model. So because we are iterating, starting from a model, you are doing the alignment, you are determining the angular, the orientation, and then you iterate to get better maps. So that's what. So where does it start? Means how do you get the first map? And sometimes you can ask, do we need a model at all? Why don't I just use a sphere or cylinder and so on? And which is the best kind of 3D map to use? And is it okay to use one, or do we use different maps to start refinement? So where do we get starting model? So if you're lucky enough, like in ribosomes, then you can look for a closely related sample, and then you can start from there. Like Elena was telling, you can start with the E. coli ribosome for a eukaryotic ribosome and so on, because the overall shape is kind of very similar. Or otherwise, you can calculate the first 3D map using 2D projections. That's very common. Or if you had a PDB model from X-ray crystallography, this can be used, but you have to be very careful to filter it correctly to avoid model bias. Again, this was explained yesterday, what those guys did to get very nice map, which was rubbish. So you have to remember this in particular. So before, I thought I will show a couple of slides of 2D class averages. So this one is of bovine ATPase from John Rubinstein. I think I got the year wrong. So it was done in 2003. I put 2012. So anyway, so the thing to remember is, so when John, he spent a lot of time. So he was working with Richard. This protein, they were starting at 5 milligram per ml. In principle, you should see a lot of them. So he spent like 3-4 months without seeing anything on ice. So then Richard and John, as they tell me, they spent like 3 days continuously on the microscope making grids after grids after grids. Eventually, they found out how to get these particles in the ice. So mostly it was to do with how you glow discharge. Anyway, the thing about what I want to show here is that this is the class averages, and you can see the ATPase. Here's the F1 domain, the stalk, and then the membrane domain here. So you can see that this classification was done with eMagic, and then you can see that some of the classes, they have kind of mirror images. So this was done on ice. So you have 2 surfaces. So a program, like any program, when it does 2D classification, it should be able to separate this. So you can see most of them. So using this information, he was able to get a 3D model. So this is one example. The other example is one of the protein I work, which is the acetylcholine receptor. Here you have a very preferred orientation. You see only the top and the side views. Then if you do a class averages, you get only one. So you pick particles, you have a lot of particles, and then you give it rely on, you say, get me 50 classes, it puts everything in there. It doesn't matter whether it puts 1 or 2. What I was looking for is, because the top and the bottom view, so if you're looking from the top or the bottom, because this is a heteromeric protein made of 4 different subunits, they have some kind of handedness, because you have alpha, beta, alpha, gamma, and delta. So the top and the bottom views should have some handedness. So in this case, from these images, the program was not able to distinguish between these 2, which means that this was never going to work in terms of getting high resolution map. So these 2 are examples which you can already decide based on micrographs and the class averages before you do anything, whether it's worth doing. Okay, so again, this is very familiar to you, the DUCs, the projections, the Fourier transform in 2D, and then this central sections. So again, the challenge is to determine the angular relation between these projected images and the 3D specimen. So this will come back again, and this forms, I think, most of the central thing of how you get initial model. And the other thing you remember is, you can get always a 3D volume from any data. You take noise, and then it's possible that you'll get some kind of a blob. So that's always remember. So here are some of the methods, how you can generate initial model. So the first 3 are based on tilting of specimen in the microscope. So you can have random conical tilt or orthogonal tilt, which is a variant of random conical tilt, or you can just do tomography, which is swinging the stage from -60 to +60. And the last two are based on images and projections. So you can have common lines, which in Fourier space, again, Elena spoke about this yesterday, and in real space. The last one is Prime, which was written by Hans Elmlund, which again just uses images to calculate initial model generation. I don't think I am an expert in all of them, but I will try my best. So Elena is an expert in common lines. She worked with Marines. If you have any questions on common lines, you can ask her. Okay, so what is random conical tilt? So you have specimen. These are the projections. The incident beam is coming through here. So most often you get kind of preferred orientation. So what you do is you take two images. So the idea is that particles, projections of particles are related by in-plane rotations. And then if you tilt the stage or the specimen, then you have a different view of the same specimen. So you record two images. The first one is tilted at about 50 degrees. The second one is at 0 degree. So you have to remember that the second image is more damaged because the first one you are taking in low dose, but the second one will have double the dose. And then you calculate the in-plane rotations of the untilted specimen first, and then using that, because you know the tilt angle from the microscope, you can define the relative orientation of the tilted projections. So that's the principle. This was developed by Michael Rademacher in 1980s, late 1980s. This was very popular. And one thing you have to remember is because you have 50 degrees and 0 degrees, you don't cover all of the Fourier space. So you miss something which is called the missing cone artifact. This is to remember because you can have, in the map, you can have things which are not kind of anisotropic, like you saw again yesterday. So this is a typical procedure, what you do in random conical tilt. You have a tilt pair of two micrographs, one tilted and other ones. You pick particles on the coordinates. You determine the tilt axis in both images and tilt angle. The second step is that you box out and rotate each of these micrograph so that they are in the tilt axis. Then you take the untilted particles, you classify them, you get different classes, and then you center the tilted particles by aligning with the corresponding the untilted particles. So then you do 3D reconstruction of only the tilted particles. You don't use the untilted ones anymore. So this shift is 0 because we have already centered it. And then you get the phi, which is in-plane rotation from here in the classification. Theta from the tilt angle, which is determined from 1 here. And then because we have rotated already the tilted particles to the y-axis, we have 0. So this is how you generate a model. So this works better if you have biased orientation in the grid. It's technically demanding because you have to take two images. So in negative strain you can do that because the damage, although happens, it's not kind of visible. But when you're doing that in cryo, if you want to collect a 50 degree on a 50 degree image, tilting is very difficult because you also have other problems because you have copper grid or carbon which expands and so on, so you have other troubles. So it is said that it is the only technique where you may get the correct handedness of the calculated structure. I put may here in red because this is not always true. Because if the resolution is lower, then when you go for refinement, it's possible that it's not able to distinguish between the right and the wrong hand. I will show an example in the end where this was the case. So this is random conical tilt. And you have what we call orthogonal tilt. So in random conical tilt, you are tilting 50 and 0 degrees, but in orthogonal tilt, you do 45 plus and minus 45. So you get a difference of about 90 degrees. So this was introduced by Andre Lessinger and Eva Nogales to overcome this missing cone artifact because you are kind of covering all the Fourier space. So yeah, so I think otherwise it's very similar. So instead of using with a 0 tilt for classification and alignment, you start with one of the tilted images and then you get similar. So those are the tilted, and so for the orthogonal tilt, it's similar. It's very demanding again, plus and minus 45 degrees, not easy. Then the one of the tilted images used for classification. That's the difference from the random conical tilt. The other method for determining the initial model is using tomography, because you are tilting already. So then you can pick the particles, you can orient, align, and then you get a map. So this I won't go into detail because you will hear more about tomography next week, and he will go into subtomogram averaging and how you get methods. So these three methods are based on what you do in the microscope by tilting the specimen to get an initial model. Well, again, we come back to this projection size theorem. So Tony Crowther in 1971 were the first ones to, or even before that, Aaron Klug and David Desrosiers, they were the first one to realize this, that you can determine the orientation of the particle by a set of pairs of common line in a 2D transform of any symmetrical particle. So Tony used that for tomato bushy stunt virus in 1971. Again, this is what we saw yesterday, iteration, but what he used was to use the symmetry of the virus and to find the common lines in Fourier space to get the orientation and then refine iteratively to get the model. I would recommend highly to read this paper of Tony Crowther to get a view of how they did things in 1971 and how things have improved now. So you can do that same in real space approach. So this was actually advocated, I think, from the early days by Martin Van Hill a lot. So in any 2D projection of a 3D object, have at least one common 1D line in projection. So if you think there's a line of a 2D projection. So once you have that, you can calculate a sinogram of this 1D projection of this 1D projection line of a 2D projection around 360-degree rotation. Then you can calculate a correlation of the sinogram, and then you can define the angles. So this is a picture I took from a review which was written by Marin and Elena and others. So this object here is a 3D representation of a D5 symmetry, and these are the projections. And you can clearly see here the 5-fold view of this 3D object. Even in 2D, you can see the same. And you can also see the 2-fold views of the object. So what you then do is take this 2D projection and you calculate 1D projection image, which are called sinograms. So once you have them, then so here are 3 different projections and 3 different sinograms, which are A, E, D, and F. So then for each of this line, you calculate a cross correlation, and then you find peaks. So here, because of the symmetry, you have these black dots, which are the 20 peaks, because D5, you have 10 different projections, which are already counted. So you have 20 peaks. So, and then you use other 2 projections also to calculate, and you have 3 different images, which together can give you a initial model. Again, I recommend this review because it's very, I think Marin has a lot of humor, and he has compared also how angular reconstitution compares with random conical tilt and other methods. So this is highly recommended. Okay, so some of the important things to remember when you're doing common line in real space is that you need to have high signal to noise ratio, which means you need to have good class averages. So if you have poor ones, then you're not going to get anything reasonable. And again, large number of good classes in distinct orientation. So depending on the symmetry, you need to have more than 2. So 3 is kind of minimal. It's better to have more different distinct orientation. And again, on the same origin, which is always not achieved during 2D classes. Okay, so the last one, which I should admit that I completely don't understand, but I thought I will just put it so you can go and read. So this was written by Hans Emlund, what he calls prime, probabilistic initial 3D model. So in a normal way, what we do is we have images, and then you calculate class averages to increase the signal to noise ratio. You get an initial model, which is like a blob. You refine, you get it. So what Hans recommends is that you don't do any of this. You just take the images, then you get a model. So the way what they do is, so in this way we are giving, for each particle we are giving only one orientation as, so like we saw with like maximum cross correlation yesterday, we are just looking at one single peak here. But in probabilistic, we are trying to give, we are kind of trying to weight them, and then you try to weight based on the correlation, the highest peak and then the highest weight, and so on. Then you calculate 3D reconstruction, which is a weighted averages of images assigned to each orientation. So each image with different weights or multiple copies of the same image can be used in 3D reconstruction. That's the main difference as I understand. Okay, so here are some of the formulas. So what it does for this 3 orientation is that it tries to search all possible orientation in all possible combination for all the images using stochastic hill climbing. Then this is the way how they calculate individual scores for a particle. This is the correlation between the image and the reconstruction, and this individual score is then used for a global score. This is one for only one rotation variable for theta, but you have to determine for the other 2. So this is the workflow what they have. You start with images which come from other sources. It could be phase flipped. Then you set up low pass limit, which is always good. And then here is the important thing, because they start with a sphere, not with anything. And then they randomly assign orientation. And then as iteration improves, they get the best model. So this loop here is for reconstruction. This loop is for finding the coordinates. So it goes in cycles, and then when it finds the best one, it gives out. So the example shown here is for ribosomes, beta-gal, I think proteasome, and so on. So they were able to get it. This is becoming very popular in terms of generating initial model, because all you do is you give the particles, give the pixel size, you sum it, and then you will get a model. So that's why people are very keen on using this. Okay, so I thought I will give you this example of complex one, which I did. This is a micrograph class averages, and then I calculated with E-man the initial model. So it looks like L shape, which of course you expect because you can see them in the images. But what you can't distinguish is which one is a matrix, which one is a membrane arm, and it doesn't have anything else. So in I think a while ago, Michael Rademacher also did for the complex one by random conical tilt. So here is a 45 or 50 degree tilted image, and this is the untilted. Then he did with random conical tilt. He could get also this best map. Funny enough, both of these maps were wrong-handed. So the way we found out was after refinement, because we knew this horizontal helix, which is unique for complex one, was on the other side when compared with the crystal structure. Then obviously we flipped the hand, we got it right. So this just shows that if the resolution in the initial model is low enough, then you will not be able to distinguish the wrong or the right hand. And of course, we did the tilt pair of the complex one to show that we had the right hand. Okay, so that's about, okay, so I forgot. And again, I thought I will show, because I didn't do tilt pair for this. So this is again very familiar to you now. I've shown it 2 times. This is from Nitish, so micrograph and the class averages. I got the initial model again from E-man using the C3 symmetry. Then once you refine, you start seeing alpha helices. And then because we can dock the model, we know that the hand is right. So once you reach sufficiently high resolution where you can see pictures in alpha helices, then maybe the tilt pair is not essential. Those are 2 examples where tilt pair was used and not used. Okay, so to summarize on the initial model, none of the methods are perfect, so you have to be careful. They don't get it all the time right. When you have low symmetry and small molecular weight specimen, this can be particularly challenging. And then it's always used to use any prior information, biochemical or crystal structure, and other validation methods. So if you think that your gel filtration says it has to be a dimer, then of course you look for it, but the images may tell it's not a dimer, it could be a tetramer, but no, trimer or something. So this is always useful to remember. And each stage of the process, you should be very critical. Okay, so these are some of the classic papers for in terms of initial model generation. So you can read all of them, or you can pick the ones you're likely to use. But I think I recommend all of them because then you have an idea how it was done and how it's still useful and so on. Okay, so I come to the last one, which is movies and motion correction. I think I'll just take 5 minutes on this and how you get high resolution map. So what I mean by movies is, so this is an image of a hepatitis B virus, which was the first sub-nanometer single particle resolution determined by cryo-EM. So we use it as a test specimen. This is about 4 megadalton. We took it on a Falcon detector. You can clearly see them. So the dose we used was 25 electrons per angstrom square. The number of frame is about 33. So when I say frames, what it means that image is a summed image. And each of them have single frames here, which then add up to give this image. So these single frames, which is about 0.6 electrons, they don't have enough signal. Maybe you can see the carbon edge here. But once you average about 9, which gives to about 5.4, then you can start seeing particles. So this is what you use for alignment and also tracking the movement of particles as the exposure increases. So this is an example of how you track. So the particles as well as the noise are labeled here, and then you computationally track what is happening during the exposure, how it moves. Then you can, in principle, correct them. So for bigger particles, it is easy because there is enough signal, but when you have a smaller particles, it could be tricky. So what we found during this analysis of this movement was that here on this axis is B factor, and in this axis is resolution. This is the number of frames, and each frame has about 1 electrons. You can see that this region here has lower resolution and higher B factor, and then there is a plateau, and then again it degrades here. So this we know because it's radiation damage after about 10 or 12 electrons. This we can explain, but this initial fast movement was not expected. This we think is happening because when ice is frozen, it's under stress. When electrons hit, they kind of jiggle, and that's why you get kind of blurring. So ideally, a good image will start with a B factor somewhere up here for the first frame and then goes down like this. That will be the theory. This is a problem which has not been solved. So many groups, what they do is throw away these first two or three frames and then use only this one here. Or the way it's implemented and rely on is that you downweight this one and these ones, but you give more weight to this, then you can get better resolution. So this is true for many different specimens, whether in ice or in carbon. Here is an example of 2 ribosomes with different dose, complex 1, where you see again the same plot. And for beta-gal, which was done with free align in a different way, you can see the resolution is poorer in the first frames, and then it goes down. So when you are doing this weighting, you should see this kind of plot. If you don't see it, then you know that something is wrong. So what this weighting and alignment does is that in the summed image, in example of hepatitis B virus, we started with 4.9 angstrom, and then after alignment it increased, and then after weighting it goes to about 3.9. So this was done with less than 1,000 particles, about 3 hours of microscopy. Okay, so these are some of the references which are for general reading, a lot of reviews, which are very useful if you are starting with microscopy, electron microscopy. So please do read it, and thank you.
Thank you, Vinod, for a very nice talk. Questions?
Hello, Vinod. Nice talk. I wanted to. I'm just curious about something. In the slide that you showed, the Emslund method of generating 3D model. I'm just curious whether you can use this 3D model and supply it to the initial model generation in the the other method. As an initial model, the generated 3D model in the Emslund method, and you can use this as an initial model in the first method that people follow.
You mean the conical tilt? No.
If you can go to the slide.
So this is one method where you use the projections, and this is a method where you tilt. So you are asking, can you use the model from here for the other one, or
the M-Stone method that you, the probabilistic method.
okay? So that one, Hans recommends don't do anything, just give the images.
That is okay.
Yeah.
So you get the 3D model from that method.
So the reason why he doesn't recommend is that he thinks that giving one single reference is a bad idea.
Okay.
So he thinks you have to determine everything from the images and don't give any external.
So my question was, whatever model is generated from that method, can you use that model as an initial model for other?
Yeah, that's what we do. So you can use a model from simple or prime, and then you can use it for refinement in others. Yeah,
Okay.
you can do that. Yeah.
Thank you.
Sorry, thank you for the nice introduction. And I have also a question about this picture. Since when you call it tilted specimen, it's very common, tilted specimen.
Yeah.
I mean, and then you have a very common problem with the Z height. I mean, the
Yeah.
sample height.
So that's why I think people generally are very hesitant to do this.
Yeah, then in every way that maybe can be calculated. I mean, when you have certain 40 to 45 degree Holder tilt, then you can actually calculate roughly this and the change of Z direction.
Yeah, that's used in the program too.
Using the program
Yeah.
to compensate this Z
Yeah.
and maybe try to refocus again.
Yeah, CTF find also, when you have a tilted images, when you do the CTF find, it has a parameter to determine the CTF tilt also.
Yeah, but that is afterwards, right? That is after you get image.
Yeah.
Since you get only a few chances to acquire the shoot, I mean images.
Yeah.
So I mean, for after tilting, you know the angle in holder, alpha degree,
Yeah.
alpha tilt, and actually you can estimate how much change on Z direction on the specimen, and you can tilt on the electron microscope directly, change it back or change it back. People doing this already?
Yes, I think I understood, but we can speak later. Yeah, I understand, but you were talking, you tilt to 45 degrees and then...
Change Z also, optimize.
Oh, the Z height.
Z height, yeah.
Oh, no, I think people, I don't know anybody does that. No.
Okay, but I personally I won't think that's very difficult. I just
Sorry?
I don't think it's very difficult. I mean, it's could be optimized during the experiment. I mean, yeah. Yeah.
We'll speak later.
Sure. Thank you.
I have a small question. So the series of images that you showed in various sizes of macromolecules in exposure that you showed, big to small, including Richard's hemoglobin, isn't it? So those were all taken at the same magnification,
Yeah.
60 or 50?
Yeah, 1.7 angstrom sampling. So we took it because to show us a demonstration or put it in a review so that
all were at 50,000 angstrom, or?
Yeah, all were same magnification, same dose, same
50,000?
Yeah,
around?
same detector, same dose.
Same dose.
Maybe defocus was different, but different microscope, but same detector. This was just to show what you can see, because generally people ask, can you see a 20 kilo Dalton? Then we thought it's useful to have this and then say, here it is. And then if somebody gives me, I have a 200 kilodalton protein, here, look. Then if things don't work out, then I can say, this is how it looks like.
Smallest was the something you showed.
14.
14 kilodalton, and that was looking like a dot. That's
Yeah.
it. Good. Yeah.
So basically for the handedness,
Yeah.
In using RCT, what is the limitation of resolution?
It's the limitedness. Oh, okay. So that's to do with how well you can orient or how well you determine the orientation of the tilted images. The handedness, I think it's very common to get it wrong. We have had examples where the images were noisy. We took a map from a EMDB which had the right hand. We put it in the refinement program. The hand was changed. So that can happen when you have very noisy images. So then, so we low pass filtered first to 60 angstrom. Then we had to bring it down to 40 to get it work.
So up till 14 we can get the right-handedness.
No, it's not. I think it depends on specimen. And in 3D EM, somebody was asking, and they had to go low to 20 angstrom.
So then my second question related to this, how many different orientation in least number of orientation we need for reconstruction?
You need as much as possible.
That
I think
you-
she showed yesterday.
that
You can get a reconstruction even with few, but whether you can interpret the map reasonably well is a different question. I think I have an example somewhere on my laptop. I can show you. You can interpret the map for me if you want. It's very bad. So.
You might remember she showed an elephant.
Yeah.
Yesterday I spoke
Swami.
I wanted to know if there are any practical differences between RCT and orthogonal tilt, because since you mentioned that the missing cone effect is not there in orthogonal tilt,
Yeah.
almost everybody would be wanting to do that over the RCT.
Yeah.
But are people still doing RCT, and if yes, then why?
As I know, people don't do any conical tilt at all nowadays. Simply because of the detectors, you get enough signal in the projections. They just do common lines, and that's how I think. But or the other thing people do is do tomography, which is much more automated instead of doing that. So I think that has gone down in.
Okay, thank you.
How do you go about picking particles? Because you include part of carbon. It could be that the particle picker might pick.
Yes,
the
it will
particles
pick.
in the
So
carbon.
you saw yesterday there was a parameter in Rely on where you can play around to minimize the picking in the carbon.
But actually, sometimes it's almost impossible to avoid.
Yeah, it's impossible. So
but
the
how
most
does that affect? Is it okay to have them, or is
no,
it?
it's not okay. So the most common, even more than carbon, is that if you had a round kind of object, and then there's a lot of ice contamination which will look black. Even if it's so, even for complex one, if you do automated picking, those round ones, because one of the views of complex one is seeing from the top, which looks like round, so it picks those ice, and it's very difficult to get rid of those. Maybe even carbon you can get rid of during sorting, but so what I generally do is if I do auto pick, I go through each image, clean them up before it goes into the data, because once it goes in, you never know whether it's there or it's not there. Yeah. It gives better feeling because you know that whatever went inside is not rubbish.